So our story of chemical bonds is not quite finished because we said nothing about the factors that determine the length of a bond. We understand that the sharing of electrons in a bigger box lowers their kinetic energy, and we might guess that if the two protons in the last module that we discussed were to fall together on top of one another, there wouldn't be much of a box to spread out in compared with the individual atoms. But of course we've ignored a very important factor. It wasn't written into our Hamiltonian, and that is the repulsion between the protons themselves. So we considered only in our perturbation Hamiltonian, let's take the electron on atom 1, we considered this attractive interaction with proton 2, but we ignored completely the repulsive interaction between the two protons themselves. So in fact, to do a proper calculation, we have to include this and balance the attraction between the electron and the second proton with the repulsion between the protons. In many electron atoms, there is also the fact that the electrons, core electrons will themselves repel if they're not involved in bonding, and the Pauli exclusion principle keeps electrons out of one another's way. At least it requires that the states be orthogonal when the electrons occupy the same spatial locations, then that requires very high kinetic energy. So these factors then lead to a repulsion that opposes the attraction, and when a detailed calculation is done, so this is a calculation that we will see again in chapter 8, you see here the attractive interaction as the electron gets closer to the second proton. Here is the repulsion though as the two protons start to feel each other, and you can see there is a fine balance with the attractive interaction just winning out at long distances, but then as the distance gets closer, the interaction very rapidly becomes strongly repulsive, and so the position at which the pair of protons would sit in fact is right here where the interaction energy for the total interaction is minimal. This type of interaction potential is very general in physics and chemistry. So if I plot the interaction between a pair of atoms as a function of distance, generally of course the potential will take it to be zero at large distances. As an attraction forms it becomes negative. The energy is a minimum at some point, and then repulsion starts to set in very rapidly as the two atomic centers are brought close to one another. This point here then is the equilibrium distance of the bond. The fact that pretty much every chemical bond that you can describe by a pairwise interaction looks this way leads to the introduction of a very interesting general formula shown here on the slide, the Lennard-Jones 612 potential. Such a potential applies not just to covalent bonds, but to many types of atom that interact via weaker interactions, such as, for example, dipole interactions between molecules that have charges separated on them, and even to atoms that have no dipole moment at all, so completely uniform charge distributions, but that are fluctuating, so that at a moment in time, for example, the charge distribution might look like this, resulting in a net dipole interaction polarizing this first atom over here. Surprisingly, there are even interactions between rare gas elements at absolute zero of temperature owing to vacuum quantum fluctuations, the uncertainty principle, and the fact that the atom can still make very brief transitions into excited states even if no thermal energy is available because of delta E, delta T being on the order of h bar. All of these things put together then serve to make this a very universal form for an interaction potential. Here it is as commonly written as 612 potential. This term is positive, so it is repulsive, and this term here is negative, it's attractive. It falls off slowly, 1 over r to the 6. The 1 over r to the 12 is an arbitrary choice. An exponential is often used, but 1 over r to the 12th is analytically more tractable. In this expression here, sigma would be the equilibrium spacing between the atoms, and it's referred to as the van der Waals diameter of the atoms if the two atoms are of equal size. The quantity epsilon here is this energy minimum, and so epsilon is the bond energy for the molecule in this simple description. Many properties of solids can be calculated from model potentials like this.